Okay, well, now we've got an example where we have the points 4, 2, 3, 1, 5, -2, and 6, 4. Okay, in order to solve, or to fit a polynomial to 4 points, we can't do that with a quadratic polynomial. Matter of fact, if you graph these points, you'll see that the leftmost point, which is 3, 1, lies lower than the point 4, 2, but the point 5, -2 lies lower than that. Now that's all right. We could have a quadratic equation, our quadratic function, through these 3 points, but it wouldn't go through the last point, which is 6, 4, and lies higher than any of the others. So we could get a quadratic function that went through these 3 points, but it would, since the graph is a parabola, the parabola would keep going down. It wouldn't come back up and get this point. In order to pick up this point, we have to have a function of this form. And you should know, because calculus is a prerequisite for this course, from your study of finding maxima and minima and critical points and graphing, that you need at least a degree 3 polynomial to go through all of these points. Among other things, you would have to have 2 points at which the derivative is 0. And in order to get 2 points at which the derivative is 0, well, that's not going to happen with a quadratic polynomial, is it? There's only 1 point where the derivative is 0 because the derivative is a linear function. So for all these reasons, and I just bring all these reasons into play because I want you to see this in perspective, the equation would have to be something like, well, have to be a 3rd degree polynomial, and I choose to represent that by y equals ax cubed plus bx squared plus cx plus d. That's a very general form of a 3rd degree polynomial. Okay, so we have that polynomial. Now we plug our values of x and y 1 point at a time into that polynomial. X is 4, so x cubed is 64, so we have 64a. X is 4, x squared is 16, so we have 16b. X is 4, so we have 4c. And of course we have d. And that's equal to the y-coordinate, which is 2. For the next point, x is 3. 3 cubed is 27, giving us 27a. 3 squared is 9, giving us 9b. Cx, well, x is 3, so cx is 3c. We have d, and that's equal to the y-coordinate, which is 1. Now I say etc. here. Obviously you can do this for the next 2 equations. And again, I saw people doing this pretty well. There's a few little mistakes, but it seems to me that people are picking this up. Okay, well, we represent this by an augmented matrix. And it should be clear that the augmented matrix, the first row of the augmented matrix, which will correspond to this first equation, will be 64, 16, 4, 1, 2. And for the second equation, 27, 9, 3, 1, 1. 27, 9, 3, 1, 1. And the other 2 equations, you can pretty much shortcut these, or you can write them out and verify, but here they are. Okay, now I didn't ask you to reduce this. I know you can reduce it. So I just say etc. Now, when this is finally reduced, since none of these points have the same x-coordinate, we know that this is going to reduce to a form where we can have a 1 as, we have the 1's lined up like so with the zeros, okay? And I could describe that, but it's a form you're used to. This is one of your echelon forms. This is the upper triangular form. This gives you an upper triangular set of equations, which says that d equals whatever this number is, and these asterisks, as I hope you're used to by now, just stand for any old number. The value of one asterisk is not related to the value of another in any way except by the numbers that you get when you reduce the equation. These asterisks just stand for whatever you get in these positions when you reduce the equation to this sort of upper triangular form. Okay, the system to this upper triangular form. So d is going to equal this number. Then we could substitute that value of d back here and solve for c and back substitute all the way up. And you'd want to write the equations out and do that back substitution to be sure you understand what that means, but I think you do. Then here, we can continue the reduction. We can use this 1 to get rid of this and get a 0 here. This 1 can be used to get rid of the number here and the number here without affecting the number, the 0 that we got here. And this 1 can then be used to get us zeros here without affecting the zeros that we got previously. And now our equation can just be read off. Our solution, D equals this, C equals this, B equals this, A equals this, and we can write out our polynomial. And then we can graph the polynomial. We can verify that the polynomial does go through any of these points just by substituting the points into the polynomial we get. Okay? So, I think everybody's pretty good with this whole idea. Now there are a couple of other glitches that can come in if we do something that we really can't expect to work out, or if we just have a case where there's something wrong with our data. So we need to be able to recognize that, so that's all this purple stuff that we'll talk about in a minute.